Okay, welcome back again. This time we're having a look at the use of our geometric series and testing whether or not it has an infinite sum, because not all geometric series have an infinite sum. So the main idea here is that we've got an interval. An absolute value can be expressed as an interval between plus or minus 1 when it's compared to 1. So that is the distance from the origin in the plus r direction, and equally in the minus r direction, is less than 1. So provided that distance is less than 1, we can write is less than 1. Okay? So this is just this business here. So this is all of that along there. Okay? So we already have an idea of intervals, and we can clearly see how r is going to be impacted. It's going to be less than 1, but greater than minus 1. So our formula here is this particular one. It's an abbreviation. So let's just have a quick look at how that works. Because if we've got our sum term, and remember this is an infinite sum, so our sum term is our partial sum, 1 minus r to the n. And we're going to use the limit idea again, okay, to see s at infinity, not just some partial number, but at infinity. So we have to do that invocation again as n approaches infinity for our sum, which is going to be the limit approaching infinity for a1, 1 minus rn, 1 minus r. Now you notice that the only term that's affected here is this n term. Okay? As Rn approaches infinity. Now R is itself less than 1. As R is being raised to the power, it's less than 1. So it's a fraction. Okay? It's a fraction. And we just saw fractions. So in this case here, it goes to 0. So that's a little bit of a difficult thing, provided you remember that r is a fraction. So if r is a fraction, as it's raised to a power, what we'll end up with is, if that's 0, we just get a1 times 1. So we get a1 over 1 minus r. Okay? Now this is only true when r is less than 1, because of this up here. Okay? So all of this math sciences goes together, doesn't it? Okay? So Rn approaches 0 as n approaches infinity. Okay, because r is fractional, it's less than 1. See that? R is less than 1. Okay? Alright, so let's use this to fill in our parts. Let's see if we can check it out. So we've got our common ratio. So our ratio will be the A2 over A1, for example, which is 2.25. You can use your calculator. And we'll get a common ratio of 1.5. Oops. Is greater than 1. The sum to infinity does not exist. Does not exist. Okay. Alright, I can accept that. So the next one is the same thing, r. So therefore, minus 121 over 1.1 is minus 1.1. Whoops. So the absolute value of minus 1.1 is in fact greater than 1. So again, infinity does not exist. Okay, it does not exist. Oh, so we can use this property to test whether or not a particular sequence, an infinite sequence exists, has a limit by looking at R. So that's very useful information. All right, let's have a look at the next one. So we can check our R. Our R will be 3 over 2 divided by 2, which is 3 over 2 divided by 2, which is 3 over 2 times 1 over 2, which is 3/4. Aha! Very good. So, as the absolute value of 3/4 is indeed less than 1, S infinity does exist. Very good. So we're being very mathsy. So S infinity is going to be equal to our reduced formula, 1 minus R. Our first term is 2. There it is. Our first term is 2, 1 minus 3/4, which is 2 over 1/4, which is 2 divided 1/4, which is 2 times 4 over 2, which is equal to 1, 8. Very good. So the sum of this particular group, now we can use technology to do this, but why do we need technology when we're at least as good as Wolfram Alpha? We've learned that already. So for this one here, R is going to be A2 over A1. So it's negative 1 over 8. So it's negative 1/8. So negative 1 as negative 1/8 is less than 1. S infinite exists. Okay. So the limit for the infinite sum is incorporated in this equation. So we can be careful, use your brackets. So we've got 8 divided by 1 plus 1/8, which is 9/8, which is 8 divided by 9 on 8, which is 8 times 8 on 9, which is 64 on 9. Okay, so we were able to generate these partial sums. So do our machines keep turning? Do our planes keep flying? Do the morbidity rates on our science projects improve? Are we making a contribution to society? So this is the maths that we do to do that. All right, so that was a bit shorter. I'm going to come back and have a look at it.